Morning. Morning everybody, and welcome to Nordic HDI. My name is Robert Ludvigs, I'm CEO of Acitec, and Acitec is a supplier of print circuit board and PCB layout. Before Mr. Hogan will begin, I would just like to share with you a few practical information. 10:15 and 3:15, there will be tea and coffee served out here in the entrance hall. Here we also have a chance to talk to our sponsors and talk to them about the deals that some of them are offering during this event. Lunch is served at 12:30 and will be next to the hotel bar. It's just also in front of the entrance hall. I would also like to thank the sponsors for making this event possible. You'll find a description of each sponsor in front of you. I'd also like to thank Axcon for co-organizing, and Anders Engel, will you show it?
I'm happy to be part of this. Robert and I discussed this a few months back as we've been working together on design services, building design, and Robert and his company management stuff. So this is a great opportunity for us to cooperate on this. And later tonight, one of my engineers, Tom, will take you through a practical approach to signal integrity and PCB design. Stack up design and such in an evening event at 8 o'clock in this room.
Yes.
So it's just an hour, and I promise that it will be lightweight given the time of day. But please continue to participate at 8 o'clock this evening.
Thank you, Anders. I'm also very pleased to announce that Mr. Holden has agreed to return to Europe and host this seminar again later on in other countries as well, and also he will also like to cover other topics such as flexible circuits and also other topics. Mr. Holden's ambition is to share his knowledge and to educate people. This is why all these publications are for free. If you want, you can contact Acitec, and we also like to share with you the originals of Mr. Holden's PowerPoint presentations and so on. If you like to make a printout of the HDI handbook, then this can also be organized, but there are some rights that will need a signature from Mr. Holden to get it printed. But we can organize that for you as well. I hope you're all set up with your laptops, and I hope also everyone have power for that. No? Anyone else? Anyone doesn't have it? Okay, we organize that for you later on. Let's see.
This is the transition. Those of you that have tablets, like myself, it'll last 10 hours and can have 20 or 30 books on it. So, but a laptop you have to plug in for this thing. So, I highly encourage you that buy a laptop, a tablet. Especially the Google ones are not that expensive compared to the Apple. And you can put everything ever printed in printed circuits and assembly all in the one tablet carried around with you.
Yeah, I think next time we need to have a tablet sponsor for this. Anyway, here at Acitec we are very fascinated by HDI, and even though we've been producing HDI boards for many years, we are never too experienced to learn something new. And this is why we're very excited about having Mr. Holden here to talk about this subject and to teach us more about the techniques and the design rules for implementing HDI efficiently in your designs. So please welcome Happy Holden.
Thank you, Robert. So red light's supposed to be on? Or? No. Oh, this is not. Clip on.
Oh no, look at this. Is it working now?
No.
No, this is
There we go.
Is it working? Okay, I'll talk to one of the technicians. No. Okay.
You can probably hear me well enough in the back, okay? So this is approximately our schedule today. I'm going to force feed you about 20 hours of material in only about 8 hours. And that's because, but all the information for all 20 hours are in the book, in 860 pages. But so you've all got a copy of that provided. Since it's electronic, you can use hypertext search for a particular topic. But mostly, this is going to be in more detail than the book, or specific examples that are not in the book. So this is not a duplication of what's in the book. It's in addition to the book. And then tomorrow, we'll get into on some of the more detailed parts tomorrow. With that, let me go to our first one. I'll start with just a brief introduction about HDI fabrication process. Is there anyone here who actually is a fabricator? That's not unusual. We seem to have fewer and fewer fabricators left. At one time, the former Hewlett-Packard facility in Moltec in Germany was a major supplier of HDI. They're no longer in business, but it's changed a lot. So you have mainly only prototype people. So we'll get into that a little later today. My experience in the last 45 years, I started at Hewlett-Packard after coming back from Vietnam and getting my master's degree, was in integrated circuits. And after about 6 months in integrated circuits at Hewlett-Packard, they asked me if I would go down the hill to help solve some problems in a plant they had that manufactured printed circuits. And my question was, well, what exactly is a printed circuit? So I didn't start in printed circuits, I started in integrated circuits. But fell in love with the chaos in printed circuits. I don't know if you've ever toured a printed circuit manufacturing facility. How many of you have actually seen how bare printed circuit boards are built? Well, then you can kind of appreciate this is a terrible, terrible process that's complex and convoluted and touches on about every kind of manufacturing technology. Computer, numerically controlled machine tools, chemical processes, photographic processes, hydraulic and material processes, all mixed together where we keep dunking the things in water, which is something we should never do. We would never be able to make a single integrated circuit if we had to use aqueous processes like they do in printed circuits. In semiconductor, we're mostly dry, vacuum and things like that. We don't want water anywhere near. Water is such a deadly adversary when it comes to dimensional stability. And yet printed circuits has this thing over and over again, which is endless amounts of headache. Well, as a chemical engineer, I fell in love with this chaotic process because nobody seemed to know what was going on. It'll be, as I talked to Robert, maybe a potential future seminar, is that unlike other engineers, as a chemical engineer, I was taught a lot about statistical design of experiments. And that is, as a chemical engineer, we're barely qualified as engineers because we deal with vats of bubbling liquid that nobody quite knows what's going on. And we don't know what's going on. We're not chemists. We didn't invent the chemistry. We're engineers that we have to make tons of this stuff for a profit. That's what chemical engineers do. They just make tons of chemicals for a profit. And the word for a profit is very important. So we don't worry too much about the science of the chemistry, but we do worry a lot about the quality and use of raw materials. And because our tools aren't extensive, we use design of experiments and statistics to understand what's happening inside these black boxes. Well, to a young engineer, printed circuit plating or lamination were just black boxes. And if I treat the inputs and outputs, I can find out what's happening in the transfer function. And I can find out why they're deviating. So without knowing anything about the theory, I can still run a printed circuit process. Unfortunately, all the electrical and mechanical engineers had no design of experiment training. No reason to, because their worlds are very exact. They have tools and measurements. They deal with 10%, 0.1% accuracy. In my world of chemistry, I'm lucky if my models are 30% accurate. So I'm used to much more chaotic. And walking into printed circuit manufacturing, the chaos was something I was trained to organize. And that was my first introduction to Hewlett-Packard. And fortunately, in the early 70s, Hewlett-Packard had this meteoric rise because other than making measurement equipment, which was low volume, we introduced this thing called a handheld calculator, the HP35, which I got a chance to work on with Bill Hewlett. And marketing told us we'd be lucky to sell 300 of those a month because they're $400 US for a calculator. You know, nobody's going to, well, 300 a month is like a high volume voltmeter, no problem. The only problem is after the introduction, the orders went to 3,000 an hour. Okay, we have capacity for 300 a month. Customers are going to be very annoyed if they find they have to wait 5 or 6 months for these calculators. And so we get this crash course of expansion. The first thing, they just gave me an endless plain text and said, visit everybody that makes printed circuits and have them make printed circuits for us, so we at least have printed circuit boards, and we'll find some word assembly. And, some of the problems, the keyboard on that calculator, we invented ourselves, because the smallest keyboard for electric typewriter was about this big. Well, the whole calculator is only this thick. And so there was no reliable keyboards in 1970. And so the mechanical engineers came up with this little Klaxon Cricket keyboard, which is annealed beryllium copper, pure gold plated, parallel gap welded to a gold printed circuit board. And so we had warehouses full of XY plotters with parallel gap welding heads running around welding all these key strips to the circuit boards in order just to make the keyboard for that that unit. But that got us into automation and a lot of other areas. But like IBM or Texas Instruments or Siemens or NBLE or Ericsson or Philips, in those days the OEMs had to manufacture their own printed circuit boards. And so they could afford the engineers and the R&D. And so fortunately I had, through the education process of a large OEM, larger budgets than people have today. And the use of other engineers, masters and PhDs, being applied to problems that today we don't really have. And so, as I'll introduce, we got into high-density interconnect, not because we wanted to, but because when we developed our first 32-bit computer in 1982, we had figured out how to make three-dimensional integrated circuits. And so using a process called NMOS3, we built the world's first 32-bit processor on one chip. So the chip worked successfully. Unfortunately, when we mounted it and put it on a PC board, it didn't work. And the engineers go back and say, well, what's happening? Well, this NMOS3 process didn't have the energy to drive the inductance of a through hole. A through hole is about 15 picofarads, picohenries. And this integrated circuit could not drive 15 picohenries. We back calculated, and it could drive about 7 nanohenries. The second thing was that our signal, the signal would only run a couple of inches and then ran out of energy. And that's because we're using FR4. And so we, again, back calculated what dielectric constant did we need to get the signal across a 6-inch PC board for the other circuits. And it said that we had to use Teflon, PTFE, dielectric constant of 2.2 to 2.5. The third problem was that although it was ceramic packaged, it burned itself up and had a heat dissipation greater than a nuclear reactor. So this is the problem, this is a perpetual problem that integrated circuit people come up with an integrated circuit. When they finally decide they're going to put it on circuit boards, then reality shows up and it doesn't quite work the same on a circuit board as they thought in theory. And that's what we did. We came up with the integrated circuit and now didn't really have a way of packaging it. So we ended up creating a metal core PC board that we technically bonded the chip to with 4 layers of Teflon each side with laser drilled holes that were 0.125 millimeter diameter in depth. And that was to make the chip work. That's the only reason we came up with that, is that without that the chip would not work. So in 1982, we developed this manufacturing process in Colorado, in Loveland. And we had to build our own laser drill, we had to develop our own ion plating and sputtering method for metallization. None of this stuff is available, just in order to manufacture these PC boards. And in 1985 went into volume production. So the Japanese claimed that they invented the microvia. Unfortunately, I can show them the 1985 laser drilled HP boards that were in high volume, so they weren't invented by the Japanese. HP didn't make a big deal about it because we were instantly closed down by the US government. And that is, the Department of Defense says you cannot make these PC boards. We don't mind 32-bit computers as long as they look like axes. They weigh 1,000 kilos and are 19-inch rack. But we cannot allow somebody to make a 32-bit computer that's the size of a children's lunch pail, is conductive cooled, not air cooled. And unfortunately, our silicon process is what we call silicon on sapphire. And that is, we use sapphire and we epitaxially grew silicon on the sapphire. Well, unfortunately, that's radiation hardened. And so the federal government says, we spent $2 billion US on this project, and you've already accomplished it, and we didn't know about it. You cannot sell this computer. Well, fortunately our owner, David Packard, was in the Defense Department, went to Washington, we eventually came up with an agreement that we would serialize every single board that we manufactured, and we would visit every board every 6 months all over the world to make sure that the Soviets hadn't stolen this 32-bit computer, because unfortunately it was the ideal warhead computer. That wasn't our objective. Like I said, we were just trying to make the stupid chip work. And so that's the history of it. But one of the things that I just described to you is not a mobile phone. This is a high reliability, high performance computer. So the first thing about HDI is that not all HDI is the same. And though we use the words, and people get confused because they may be talking about consumer products like this, which is really miniaturization, which is the cell phones, camcorders, and other types of, what do they do with my pointer? This is one of the best examples in 1996. The first of the digital camcorders. This is important because you can see it's a 2 plus 4 plus 2 construction. And the entire PC board used 0.5 millimeter pitch products. So I doubt if any of you here, even today, would do a design. The other side is just as populated, all 0.5 millimeter. This is 1996. So this is what I consider one of the highest density. This is over 600 connections per square inch, or the equivalent connections per square centimeter. Right now, if you do multi-layer, you do 100 to 150 connections per square inch. This is over 600. 6 times more dense than what you may do today if you consider a dense PC board. They had to do that. Every single one of these chips had to have an interposer that was 0.5 millimeter because the chips themselves were 1.5 millimeter or 1.25 millimeter pitch. They soldered them to an interposer, and then the interposer was 0.5 in order to get everything down in the size that you've seen it. This is the same for mobile phones today. But that's not the same as Platform 1, which is high performance. High performance in areas like that, I hope you never ever see this device right here, used by the US military. And it's a chemical analyzer for chemical and biological warfare. And so this is a big laboratory shrunk down. But it also has, it's used by police departments. It has a recognition. And if they find your dead corpse somewhere, they can just put the thumbprint on the screen. It scans it and then pops up with a picture of who they just found there. So this is not your mobile phone. This is ruggedized military and police type of areas. And it uses an optical disc within it. And this goes down to 0.4 millimeter. And this is circa 2001. So this is not 2014. This is over a decade ago that military and other ones are using 0.4 millimeter, 0.5 millimeter pitch devices with that. And this is a 2 plus 10 plus 2. The second platform is packaging. This is the highest density. Today, these packages like this, they're made about 200 million per month. And this circuit board has 0.1 micron lines and spaces. Well, no, excuse me, 0.01 micron millimeter lines and spaces. 10 micron lines and spaces. So there are about 8 printed circuit facilities in the world. Their daily output is 10 and 15 micron lines and spaces by the millions, but only for packaging, for integrated circuits. The reason is that these things are no more than 50 millimeter by 50 millimeter. And the defect density on a large panel means that we would never get a single complete circuit board out the door. But with a small one, wherever the defects, we just throw those away, ship the remaining ones. But those of you that are still working with 5 mil, 4 mil lines and spaces, 0.1 or 0.125, you got to remember, your competitors may be working with 0.01 millimeter lines and spaces. That's the current level, not 0.1, but 0.01. And so tomorrow we'll get into, well, why aren't you using 2 mil or 1 mil lines and spaces? Everybody else is. That's an interesting question. And that's because, but this is platform 2. Now, interesting enough, none of these are built on FR4. So we're going to talk tomorrow a little bit more about, well, what material do they use? Because you can't do 0.01 millimeters on FR4. The weave of a laminate restricts that, but there are plenty of new materials. And ones like this is for telecom here in Europe. This is a video encryption system for base station, so that you can look at the internet and watch movies on your mobile phone. Well, the reason is something has to encrypt that signal at the base station. That's what this guy does. And again, it's just a 4-layer. But this thing operates at 190 degrees Celsius. 190 C is its operating temperature. So this is like oil and gas. This is high reliability military type HDI boards. And this is all polyimide film with a heat spreader. The last one, the platform 3, is more than likely where most of you are. And that's high reliability, high performance PC boards for automotive, military, telecommunications, medical. This is not the same kind of HDI that's in your mobile phone. And because they need to have different materials, different design rules, and different boundary conditions, these are 3 distinct different markets of HDI that use different design rules and different materials. But unfortunately, there's not really books out there that point out that these are different. If we all call it HDI, you can get confused about, well, what material, what design, why. So hopefully in the next 2 days we'll sort all of this out. This PC board is particularly important to you if you've ever flown on the Boeing 787. This is the optical controller board for the Boeing 787. The 787 is a plastic airplane. It doesn't have any metal in it. Consequently, it does not have any copper wires in it. It's all fly-by optical conduit. So it's fly-by-wire, but the wire is optical. There are no copper in this plane. Since there's no copper, there's no shielding. And so these sets of boards have to be inside of ferric shielded boxes because the skin of the plane is plastic and things like that. Well, when they came to me, this was 20 layers, twice the size, and their question to me was, we can't complete the design without using microvias. How much will the board cost at 20 layers with microvias? And I went to my models, showed them what it would cost. My question was, what kind of board are you designing? Because I've never seen a 20-layer microvia board before. They gave me the parameters, and I said, well, my modeling tools say this should only be 10 or 12 layers. And they said, that's impossible. We're at 20 layers now and we can't finish. How can this be done in 12 layers? I said, well, pay me and I'll come down and show you how to do it. Well, so they did pay me. And 4 days later, we had this. They were 18 weeks and not finished with the through-hole design. In 4 days, we finished this design. And that's because the HDI, as we'll see tomorrow, is infinitely easier to design if you know what you're doing than a through-hole board is. Consequently, the board went from 20 layers to 10 layers and shrunk in size. And we completed the other 70 cards in the cage in another 2 weeks. They were now 4 months ahead of schedule, but more important, they had saved 1.5 kilos. Well, Boeing was paying $1 million per pound to save weight, and they just saved almost 3 pounds. That's $3 million bonus. Unfortunately, they gave all the engineers a signed certificate of appreciation, but kept the $3 million for themselves. They didn't hand it back to the engineers that did this. But one reason is that this one, you notice there's no traces. We moved the ground planes to the outside and formed a Faraday cage. And because of the Faraday cage, we didn't need the steel enclosure and went to a plastic molded one because this board is totally silenced. So these are some of the advantages. HDI, properly designed, it has better signal integrity, less radiation, can be thinner, lighter in weight, can be much smaller and much fewer layers. And in this particular case, 60% cheaper than the through-hole it replaced. Now, unfortunately, that's not the norm, because everybody here knows how to design through-hole boards, and I guarantee you, even though you use micro-vias, you may be using those micro-vias as small through-holes, and it's still a through-hole board. This is not a through-hole board. And we'll talk about it this afternoon as a case study in terms of what they started with and what they ended up with and why. Why could, at 10 layers, this thing handle the density that they couldn't do with 20 layers? And you'll see it's obvious when we get into it. There's probably a fourth platform. And the fourth platform we'll talk about tomorrow, and that's embedded components. So we'll talk a little bit tomorrow about embedded actives, in which we put the IC inside the PC board, and we connect to the IC through laser drilled blind vias. But the integrated circuit or the components are inside the assembly. And that's probably an emerging fourth platform of YHDI, albeit, again, a special one. If you look at HDI, overview of the HDI processes, this is in the book. There are about 14 different HDI processes. In North America and Europe, we use one that we call HDI. But if you go to Asia, you will find 12 different modifications that we'll talk about tomorrow. So there's a lot of different HDI out there. Most of this is packaging or consumer product. The HDI we talk up there is medical, telecom, aerospace, military, is kind of the replacement of high performance multi-layer. Down here, it's more the area of miniaturization. But I had to put a material code, because you notice right here in the colors codes that only the light green is FR4. There are these other materials that we'll talk about today and tomorrow. That's important for you to consider if you want costs to be less and performance to be higher. Is you've got to move off of FR4. The problem is the glass weed. That creates discontinuity in terms of dielectric constant, but it also impedes high frequency signals and promotes CAP and other types of reliability problems that we don't have, because we're going to move things closer together. And we don't want to worry about CAP when we move things closer together. And this group out of this line right here, this group down here uses no electroplating. The vias are all solid. So I've broken this up into type 3 staggered, type 3 stacked, and type 6 any layer. Because this group down here is what we call second and third generation. There's no electroplating. These holes are not hollow. These vias are all solid. So you see, bump connection, sheet copper, or photo or conductive paste form up all of this group. This group up here uses conventional electrolytic processes that you have in through-hole. But obviously this construction down here cannot be duplicated in multi-layer, as you would think of them. And so that's the whole changing world of component and 100% surface mount. So a laser blind via is just these lasers drilled, in conventional FR4 with conventional plated through holes. The manufacturing process is nothing unusual. Laminate the thing together, conventional drill, laser drill, and metallize. So this is your lowest cost HDI, in which we just put blind vias either side of a conventional multi-layer. And you can do a lot with this architecture, as we'll talk about tomorrow in design. There are additive metallizations, in which it's fully additive, but that's still a chemical makeup. The lasers used are typically certain types of infrared and ultraviolet lasers. These are the different wavelengths of lasers. And